Okay, so I hope you can hear me.
Yes, sir, I can hear.
Okay, so let us start the first week. So this is week 11 of the natural language question. This is our second last week of topic session. And the instructor of this course is Professor Pawan Goel. Course code is NOC 22/98. This course is conducted by Indian Institute of Technology Kharagpur. And I am Punyajoy Saha, who is your teaching assistant for this session. This week we are going to cover important topic of text summarization. So if we go by the definition, a summary is a text that is produced from one or more text that contains a significant portion of the information in the original text, and that is no longer than half of the original text. So although the definition is not much clear, the idea of a summary, as we also might know, is to provide a succinct, like brief text which includes all the details of the or includes the overall idea of a text, but is very short in nature. And this has many applications in real world because whenever you search something in Google, or the first thing that you get is a summary or like a summary of the answer. So, and in any, like, if you are going by articles, the heading of the article or like the small subtext of an article, let's say in any media, newspaper or something, is a summary. So those things are very important because this helps in compressing the information. And at this age of like information overload, we expect the summaries to help us in a way. Now we will rightly move to the questions. So question one is, what are the ideal qualities of a summary in an automatic extractive summarization? So here the main thing is that we have to identify which one should be maximum, which one should be minimum. So the first option is maximum relevance of summary to the theme of the document and maximum redundancy information. Minimum relevance of the summary and then minimum redundancy, minimum relevance and maximum redundancy, and maximum relevance and minimum redundancy. So which one of them will be the correct answer? So remember in summarization, so what is the main motivation or main importance of a summary? So try to think in that way. So what will be higher? What will be lower? So what will be the answer to this? Like which one should?
The option 4.
So option four will be the minimum. Option four will be the correct answer. So maximum relevance to the theme is the basic goal of any summarization method. That is the maximum goal, maximum like saturation maximum, and the redundancy should be uh, less. So the next question. So imagine you are summarizing a document of 5 sentences using Lextank algorithm. There is an algorithm where you have to get an extractive summary. We have found the following similarity metrics that we already have, and now you have to where Mij is the similarity between sentence Ti and Tj. So what is the row stochastic version of this matrix? So what is the row stochastic version? So simply put, we have to normalize individual rows with some of its elements. So let us try to do it for one row. So row 1 sum is 1.1. If you sum this zero point 0.5, zero point 0.4 and zero point 0.2, it is 1.1. And after normalization, this row will become 0.0, 0.5 by 1.1, and this way. And this will be some value. So this is very simple task. So let us just try to do the normalization for this matrix in your workbook or something, and then we will try to see the answer. So what will be the correct answer? So can you calculate for the other rows? What will be the stochastic version? And it will be one of those three options. So let us try to calculate the matrix first, and then we will try to see what are the options. Yeah. Uh, but yeah, just try to do that. Let us give like 2 3 minutes to this. Uh, have you calculated it?
I still don't.
Okay. Let me know once you're done.
Yeah, I've done.
Okay. So, yeah. So which one is the correct option?
Looks like the third one at the
This
left
one.
bottom. Yeah, it is.
So this is the correct option. So did you?
Yeah, I got that. Yeah. But of course, the rounding of possibly is some.
Yeah, yeah. That is fine. So any doubts?
That's fine.
Yeah, so this is very simple. So you have to just subtract by the like divide by the sum. The next is find the page rank values for the uh, five sentence notes mentioned in the above question. So these are essentially now these things are now sentence notes that have that is like a graph, you can say, where each sentence has a link based on the probabilities. It has a link between. So this means sentence I and J are connected. So something like that. So or the similarity. So basically they are connected by their similarities. So now what you have to do is we have to find the page rank and we use mu equal to zero point 0.5. So what is the formula for that? So you can either refer to this formula or you can directly refer to. So basically, you have to multiply mu into the dot product of v, that is randomly initialized vector, and the similarity matrix plus 1 minus mu by total number of sentences. So this part, so this is done because sometimes what happens is during a graph traverse. So this everything. So this is like a. So this is what we are trying to do is we are trying to find this vector v that will tell us the importance or the information of each of the sentences. Now to do this, we will do a random walk. So random walk means if we have a graph of connected sentences by their similarity, we will start from the first node and go to a random node. And in this case, what happens is in any of this situation, it may happen that in a node there is no outgoing edges. So that means the random walk will stop. So for that, we will use a probability value so that even if there is something like that, like there is no outgoing edges, we can, with some probability, we can shift to some other node to continue the random walk. So that is basically the function of this part. But overall, the formula is this. Now you have to multiply. So we will start with a v of v. You can start with anything.
Can you quickly talk about SM and things in the formula? I don't remember.
S is the number of sentences. So if
Okay, it's 5 here. Okay.
yeah. So basically, we are so this is the probability, uniform probability of from a node. So if from a node we can go to any of the sentences. We can, so basically this is teleporting. So we can from a sentence S1 we can go to any of the other sentence. Now the and the probabilities for going to any of these sentences is equal. So that means it is like 1 by S, 1 by number of sentences. So by that probability we can go to some other sentence.
So what is the probability part in this equation? Mu is mean. S is the number of sentences.
Mu is not mean. Mu is the like uh, which one part do you want to focus on? So if I let me show.
Yeah, where I'm getting confused is if it's probability thing and the random walk
Yeah,
happens in a random fashion, then the answers could vary from iteration to iteration, right? Any past.
that will not. Let me show you. So this is the part. So let's say, yeah. So this is the part of the lex rank algorithm. So this way, let's say the graph is connected. Okay. So from each sentence one, we can go to some other sentence with some probability. with some similarity value. Like the similarity value is if the similarity is 0, then we cannot go to from S1. So these are default 0, and so from S1 we cannot go to S2. So that is, sorry, S3 we cannot. That is 0. This is the way the graph is there. Now what we have to do, you can see the screen, right?
Yes.
Yeah, so now what we have to do is, now let's say if we are here S1. Now we want to go to some other node. So with probability 0.5 we will go to 2. With probability 0.4 we will go to 4. 0 yeah, we will go to 4, and with 0.1 we will go to 5. So these are the different probabilities that we will use when doing the random walk. Now what happens? So let's say this is S5. So S5 has all the incoming edges, for example. Now you cannot leave S5 and the random walk will stop. So the idea behind is that the random walk will continue, and finally what we will get is that Ij will become equal to Ik. That is the information that we are seeing here, and this information will become equal. And at that moment we will stop.
No, can we just hold a minute? S5 is having 0.3 probability to go to 1 and 0.7 probability to go to 4.
Hmm.
And this is not directed, right? So why are you saying it's incoming, or is it?
So I am considering a
Yeah,
hypothetical
Raju.
situation. So see, for example, this is 0.7, and from S5 to S4 it is 0.7, but from S4 to S5 it is 0.2.
Correct.
Right. So this can be, if it is 0, that means there is you can go in only 0.7 direction. Like if this is 1 and this is 0, so that condition it is become directed.
Oh,
And instead of directed, it is like there is a probability associated that you can.
oh,
So ideally, in like very vanilla fashion, it will be like 1 or 0 to denote if it is directed or undirected. If it is undirected, you can travel from either one of those, so it will be both ones. But in case of directed, it will be either one and another 0, or both 1, or this one and this one 0.
oh.
But the purpose of this is different. So this is when there is coming edges only, and you want to continue the random walk. So that is the correction that we.
Okay,
But
so there's some probability with which there is incoming. So
the
now, if you
variability.
take a random walk,
Hmm.
sorry for interrupting. So if you take one node and then look at random walk, how does that happen? In the sense, if you are taking S5, so it either goes to S1 with a probability of 0.3, and the randomness comes into picture because at the probability of 0.7, it can go to S4.
Yeah.
So that is what it means as random. Okay, got it. So thank you.
Yeah, and the doubt you are having that it will be variable, like the iterations can be variable. That is true. But our final goal is not to get the path that the model has traveled or the agent has traveled, but to find this information score. So that will always converge to a similar value. So the
Okay.
final value will be always like it will always converge. So that is the idea.
Yeah.
Anyway, so that we have to do. So they have specifically asked that we can use some Python to solve this question. So let us try it. So I have written the array here. Yeah. So I have written the array here. So this is the same array that you just now solved. And then we are starting with v equal to np.array this. And I have started with 0.2 everywhere. We can start with any other value. We will try to see it in a bit. Now let us try to run. So here what I have done. So I have yeah, this part is not working correct. So what I have done is I will start the process till 10. So we'll also see the transitions that are happening, and I will print the final v matrix after each transition. and here the formula is zero point 0.5 because mu is 0.5, so it is like 1 minus 0.5 by 5, so that is 1 by 5 because there are 5 sentences. And finally we are doing np dot product v and v into a, or v dot product a is our similarity matrix. Now if we do that, so finally we are assigning it to again assigning it to v, like the updated value. And so ideally what should happen is you should have a threshold, let's say a distance between v and j. If it is less than, let's say, 0.001 001, then you can stop. But for just simplicity's sake, I have done like counting. Let's try to run this. So what do you see? So first value is this. So we started with 0.2. So then it changed to this. Then it changed to this, and uh, finally it converges to this. This value is getting repeated, so we can just put a check that okay, it is equal. If it is equal to the other value, then it will then stop the program. Try with any other value, and you will see that the final vector will be always same. This is the final vector, so that is there. So this is a very easy way to do this, but in exam or some other place, you have to uh, like calculate it. What you can do now, just choose a random v value. So choose anything that you just like satisfied with, and then try to see what is after one step. So let us calculate the value after one step. Just report it. So we can just check here once value is correct or not, and then because in exam, I guess you will be required to like calculate this again and again. So it is better to practice.
We can take the values given in the problem itself. Like here, what was the value? I don't remember.
No, here v value is not given. So v
We,
you have to choose from yourself. Because the final value is similar, we do not need to worry about what value to choose. But I am saying for your like practice, you can start with a random v and then try to do the steps. So try to do till two or three, like first two steps. That is multiplication, then putting into the formula, then getting the v, updating the v, and then trying to do it again. So try to do that, and then we can just see if the values are correct or not based on this.
you are uploading this notebook, right? I mean, we need to try it out because.
Yeah, I am uploading.
Okay, thank you.
So the correct answer is this. That is okay. So that is already part.
Yeah, sure.
Yeah, but try to do the first two steps, and then we can discuss.
Yeah, the process is important. The answer will come. So are you presenting something? I'm still able to see the notebook only.
Yeah, so I asked you to like calculate for
No, I thought I'll use the code later. You anyway displayed that. Yeah, we can go.
okay, so I can proceed. Okay, so the next question is about so still this part we are doing this page rank. We are finding the information or the informativeness or whatever you say, and yeah, basically finding the page rank, and then we are trying to select. So this is the page rank values. Now, based on this, we can select the sentences that should be in the summary based on this value. So we will first select this. Then, yeah, do you want to tell something?
No, no, I was just saying we have to select the first one and then
Yeah,
not the
then
closest one, right?
the
Redundancy
yeah
needs to be avoided.
yeah this is without that. Yeah, so this is then we select this one 0.212 because that is second most. But selecting this way, it is uh, it it may happen that you are selecting the same redundant sentences. So that's why this maximum marginal relevance is like discussed, where we find. So here the main target is to, along with the information informativeness, we are trying to reduce the redundancy. So here again there is a formula that when we select the first one, so first one is always 0.251 that we have calculated earlier. While selecting the second one, we will try to select the second one in this fashion. So we will again calculate informativeness of S, that is maximum marginal relevance with, that is maximum of S belongs to D, informativeness of S minus lambda into similarity of S comma sum. The sum here is the summary. So summary here, so they only said that we will do this for the first two sentences. So here the summary till now is the first sentence. So we have to see the similarity um, from the first sentence and this sentence that we are getting. So now, so let us write this down. Yeah, so what is our V? Our V is this value. I think right. Okay. Yeah, so our V is this. Now we can do. So if we want to calculate, let's say 0, 1, I can write. Yeah, so let's say we want to calculate. So what will be the value of V1? So V1 is now V1 is, so V1 here is in information of S1. So that is 0.173. Okay, 0.173. So we are updating this value based on this formula, and then we have to do lambda, that is 1.0. Lambda is 1 into similarity of. So then we have to find the similarity of S1 and S0, or you can say S2 and S1. Either way it is fine. So what is the similarity of S1?
First value itself, right? 0.251.
Yeah. So first row. So S.
Now, again, are we looking at 0 as the index and then looking at 0, 1, 2 or 1, 2, 3, 4?
Yeah, it does not matter. So either one of you can. So it is S2 comma S1. S2 comma S1 will. So this one 0.806. check the value. Let us try to see.
Oh, okay. So it needs some time to digest. I'll go through this
Yeah,
later.
so we will do this 0.806. So we are doing, so our formula becomes similarity of S2 comma S1. So I am considering S1 as the summary. So S1 is S1, it will be summary, but our summary itself is S1, right? Okay. Did you get my point?
Uh,
So tab was not sure. So we are trying to find the summary of V1 or the new information score of V1 based on the maximum margin relevance. So what is the score? So we will first write the original score that is currently there, that is taken from here, that is 0.173. Then we will multiply lambda into similarity of S2 comma sum. Sum here is S1 because we have added the S1 to the summary. So similarity of S2 and sum is S1. So similarity of S2 comma S1. This value we will get from the matrix that we have got. So that is this matrix.
oh,
That will be 0.806. So we can do this. So that will be uh, 0.173 minus 0.806. So whatever the value this, whatever value of this, we will write it like into around. Yes, it is like 0. So minus 0.63. This is the new information score. This way you can calculate for V2, V3, V4, V5, or if it is like one from once, if we are following the same notation, so V2, V3, V4, V5. This way, if you calculate, you will finally end up with all the newer values, and then you can select the maximum one from that. So that is this maximum of S given S belongs to D. So once you calculate all these values, then you can select the maximum one. This process will be repeated again. So at that time, our similarity matrix will contain both, like the summary will contain both S1 comma S2, and
yeah,
maybe you can.
but the values are negative. So when we are saying maximum, we take a mod or
No, just the normal value.
okay, no.
So for few of them, the similarity will be 0, and that will actually help. That will make the values positive. So this 212 is basically this last row, this last value. That will be not change. That will not change because the similarity between that and the S1 is 0. Yeah, if you see, this is 0.
Okay.
Way it will not change. Oh, sorry, this is 0. So that way it will not change, and that way the maximum. So that will be the answer. So this is again a very easy question, I'd say. So I think most of the times you will be given for the first two questions, first two sentences only, because that way you can use the matrix that you have. Otherwise, you have to, I think, take the average between those two similarities, or take the maximum of the similarities from S1, S2. So this will be the answer.
Okay.
Yeah. So next is this I already explained. Like, what are the goals of using page rank and maximum marginal relevance? So what is the goal of page rank first of all?
Normally, it is to find the most referred to one, right? in this case,
Yeah, so the purpose of page rank is to find the most informative sentence. That is basically the information vector that we are calculating. By page rank, we are saying which of the sentences have the most information. And by maximum margin relevance, we are trying to create diversity. So the formula itself is uh, analyzing based on the similarity between S1, S and the summary. So if the summary and S are too similar, that way we are penalizing it. So it is trying to increase the diversity. So the second option will be the correct one.
yes, good.
Okay. So next question is, consider the following test case for summarizing a document with four sentences: T1, T2, T3, T4, and the relevance scores are 3, 3, 2.8, 2.8. So the relevance score like is a value. So the redundancy scores between each pair of sentences are given by the matrix. Here we have been given the redundancy score, and if the length of each sentence is L and we want to summarize, we want a summary of length 12, find out the optimal extracted summary. So we have to find the optimal summary or the so here from this sentence itself, each sentence is length L and we want a summary of length 12. So we want to select two sentences out of these four, so that we get the optimal extracted summary. So how to do that? Uh, Yeah, so this is the formula for that, like how to select the maximum, how to select the score for this summary score. So that is relevance of I for each Ti belonging to S and minus summation of redundancy of I comma j. So let us try to calculate this for one. So what you have to do in this question is you have to calculate for all the pairs. So all the pairs are noted here. So there will be like 60 pairs. T1. Yes, I have to, yeah, 12 pairs, and we have to calculate this value for those 12 pairs, and then we have to try to select the maximum or the maximum score that is given. So let us try to do this for T1 comma T2 for example. Yeah, so the first thing is summation of relevance of I. So rel of 1 plus rel of 2, right? And then we have to subtract the redundancy part. So redundancy of 1 comma 2. Okay. So this will be the good. So let us find the relevancy of 1 and 2. So it is 3 and 3. So 3 plus 3 minus redundancy of 1 and 2. Redundancy of 1 and 2 is I don't know. So
Yeah, 0.5, right? 1 and 2 or 2 and 1 should be same.
yeah, fine. That's why we are getting 5.5. So let us try to calculate for T1 comma T3. And let me know the answer. What?
No, it's a summation, right? If you just take 0.5 in the redundancies.
Hmm.
The second part, the redundancy of ij, it's a summation.
Yeah, but we have only what? Oh, you are saying like
The equation.
I is less than J. That we have to say.
Okay.
That is the important. So that's what. So we are only looking at the you can say
1 and 2.
the one of the triangle. So we are not looking at. So this will be the summation will be applicable if we let's say we have T1 comma T2 comma T3. So there are three sentences.
Okay. Okay.
We'll get another redundancy, that is minus red of 2 comma 3. That will be another. And here will be like another rel. Yeah, so this will be applicable then. But for now, it is only one redundancy.
Okay. Got it.
Okay, now try to calculate it for T1 comma T3. So I am keeping the cursor at this position. So here you have got the relevance score and the um, redundancy matrix.
So 3 plus 2.8 minus this is 1 and 3, right? 1.5.
Yeah, 0.5. Okay. 0.5. So that will be 5.8. So for this, sorry, 5.8 minus 0.5, right?
Yes.
0.3. So for this question, I think you can directly, since you are given the options, so you can directly do for like T3 comma T4 and T1 comma T2, and finally uh, T1 comma T2 we are done. So yeah, so this you can directly compute and then try to see which one is the maximum. So just try to see. Are you missing?
Otherwise, we would have to do 4 choose 2 or n choose in whatever.
Yeah, then we have to do like in first we have to fill like T1. So you have four combinations in first and 3 in second. So it will be like 12 combinations.
This is pretty straightforward. In the sense, we'll just add this whatever 3 plus and then.
It will become a bit complex when we like
Yeah, we have more than. Yeah,
three or like three sentences in. If the summary of length 3L is there, then you will get even more combinations. But since you are given the options, I think it can come as well in the exam. So if it is there, then you just calculate for the options that are there, and then you select the maximum one. And there can be another thing that there is none of this option, so that will be a tricky case because then you have to calculate for all.
in the sense, in any case, summary has to be at most half of that, right? So if it's a bigger set, I think then we'll have that. Otherwise, if it's just 4 sentences, we will have 4 choose 2 or something like that.
Yeah, that is true. Yeah, so that is what is written here. To find the best summary with two sentences, enumerate all the pairs and compute the scores. And T2 and T3 will have the highest score of 0.5, 5.7. That will be the highest one that you can check. Yeah, this is very straightforward. So I will add the link of the Google Colab note.
Please do it at the earliest possible so that I can.
You can even use like, uh, matrix multiplication website. Uh, that is also a possibility. But this seems a bit easier for me.
Yeah, in any case, I've just seen this, no, so it will be easier to reconnect as well.
Yeah, I have added this here. So
Thanks.
I think that's all for today.
Thank you. Thank you very much.